So in this example, I want to talk about what would happen with an op-amp circuit, a number of other sort of resistive elements that could also have done some dependent source, but we'll just keep it to resistive elements. The op-amp itself is enough of a dependent source, and then one inductor. So therefore, this is a first-order structure. Okay, we'd expect this to be a first-order circuit of a certain form. And so you look at the circuit and you're like, okay, I've got all these R's here, and then I've got an R over an L. Now I've got a sense of what I might do with this from other ideas. This is the L and R. I can't really reduce it much down beyond that, but at least I can start there. And the question is, well, I'd like to do something with this. Now I could also do this solution in many ways. I could do KCL. I could KCL at this node. And then try to figure out this node and this node and try to do some reductions and so forth. A couple other multiple ways I could play it. But one of the ways I would think about it, and you could do this in general for a larger circuit, is say, let me take this whole block here and think about what is its sort of Norton equivalent. Okay, which means I'm going to take this whole block and ask the question, what does it look like in this structure? So what is the current source in this RA? What's interesting about this further when you actually look at the structure is you realize if I get it into this form, I'm going to have this node at ground roughly, because the op-amp is ideal. Nothing was really said specifically about the op-amp gain, so let's assume it's ideal. And therefore, the other node on the other side of the resistor is also ground. So 2 volts, so if I have ground on both sides of the resistor, there's no current. It's almost kind of like that resistor doesn't exist. So the only thing I care about is IN. All right, so this is pretty cool. I can still calculate RA, which is that sort of equivalent resistance, but also I can say what is that input current. And just again, from some simple Thevenin and Norton kinds of simplifications, you can find this out that it's going to be R1 parallel R2 over R3 plus R1 parallel R2. And then Vn over R1. You can kind of see the Thevenin and Norton equivalent shift that's happening right in here, right? You can see where that would have been the equivalent Norton current source. And so you can say, all right, this is great. Now how do I begin to solve the rest of this? Well, I then say, well, I have an equivalent IN to work with. I know that V out is then just simply the parallel combination of these two conductances, which is now an RF and SL, right? And we're talking about this in a Laplace domain, and therefore I can talk about an inductance in that way. As a result, I can then also do a little bit of mathematical manipulation and call this RF and have SLR over R and 1 plus SL over R here. This was also known as talking about a typical transimpedance amplifier. You may or may not put the inductance in there, but without the inductance, it would be a typical transimpedance amplifier, and then we're getting some interesting dynamics because of the inductance we make. Notice that this tells me what my time constant is. It's going to be L over RF, which is not terribly shocking. These are the two things in the feedback loop. They tend to get, their importance gets amplified up because of the gain of the amplifier. And so then I can think that R out is then going to just be RF times a high pass response over whatever the input is. Well, that's cool. I actually have the input is then related to Vn. There's really no time dependence. It's just a bunch of R's that are changing it. So I can just simply add those things into the structure. All right. So then taking some elements and evaluating it, I can take this V out and get minus 5 S tau over 1 plus S tau times Vn. I can figure out what my time constant is 2 nanoseconds, because that's going to be an L over RF. Okay, here's your L, here's your RF. Compute the two things there. You actually get 6 milli over 3 mega. You're going to get a nanoamp, you're going to get a nanosecond kind of number. And then it's minus 5 there. So you go, all right, what happens if I had a step of 2 volts instantaneously? Well, that would now mean that my V out of S is minus 10 S tau over 1 plus S tau over 1 over S. Simplifying, that gives me a minus 10 over 1 over S plus 1 over tau. And we know exactly how to solve that. That comes right out of the Laplace transform tables. Gives me a minus 10 e to the minus t over tau u of t. And so you get a very nice step response. You get the sort of core sort of transfer function and other kinds of things very easily. And it doesn't turn out to be all that, nothing too difficult, but always kind of remember, you can always take groups of these things, simplify them down by Thevenin and Norton equivalents, And then you can then begin to start to realize, wait, at the L, I can use the Laplace methods, and I can then get everything to simplify down in a very straightforward way.